inventor of his age, it says, probably true. And you could view that through a stereo viewer. Or you could do something really cool. You could make what was called anaglyph stereo. And anaglyph stereo put down sort of red and blue imagery. And what that did was, imagine if you're looking at a white piece of paper through a blue filter. Well, everything's blue. It throws away all the light except the blue, and the white has blue in it. So if you put blue stuff on there, it doesn't change anything. So basically it becomes invisible. Whereas you put a red filter in it, the blue looks very dark. Likewise, you put the red image, it becomes invisible to the red filter. And so anaglyph stereo became popular for a little while in cheap three-dimensional movies. There's a picture of those stereo viewers. And this is a great picture because it's a stereo image of kids looking at stereo pairs in the library. And this is in the early 1920s. And the thing to realize is it gave you a certain sense of realism. So people used to use it to experience faraway places and things that they couldn't see otherwise with a reality that they don't get when they just look at an image. So for example, here's this picture of this bridge in India. So all of a sudden you could feel like you were in India, which was different than just looking at a static picture. And when I grew up, lots of us had these ViewMaster discs, okay, where you would put the discs into the little viewer and you would slide it down and you would see the two different things. And, you know, you got educational stuff. So when I was a kid, they landed on the moon and they made stereo photographs of men on the moon, which is really cool, talking about someplace you couldn't go. Or much more importantly, you could get Spider-Man, which is really good. And of course, if we had the internet then, we would have known that you could have ordered stereo porn, but we didn't know that at the time. Now you guys, you get three-dimensional television. So for you, this is hardly new and compelling at all. But it's basically the same principle of making sure that two different images are shown to each of the eyes. So here's the basic idea, all right? Two slightly different images. These are two stereo animations taken from this website listed here, where we just alternate showing you the left image and the right image. Already, if you just take a look at the fence post here, you can see that these pictures were lined up in such a way that the fence post was sort of right at the same point in the two pictures. And you can see that the stuff that's in front seems to be going that way, stuff in the back goes that way and then back again, all right? Or you can switch them. But the idea is that stuff in front of what you're verged at moves in one direction and the stuff behind it goes back. We'll actually see that when we talk about the ordering constraint 2 lessons from now. Here's a cool one that was done of somebody diving into a pool, and you can see he adjusted the images so that at the depth of where the swimmer is, the two images are exactly lined up. So the bubbles, the splash moves in one direction, and I love that the shadows on the bottom of the pool move in the other direction. So the basic idea is that from two different views, from how they move, you get a sense of what their depth is. So let's talk a little bit about stereo vision. How do humans do it? And at the very, very end of the course, we'll talk a little bit about the physiology of the human system, but today I just want to talk about the computation. If you think about it, you could imagine that stereo is done a couple of different ways. One way might be that you sort of find some regions in one image and then you find those regions in the other image and your brain compares them and sees how they've shifted relative to each other and then somehow figure out the depth. Another possibility is that maybe you just process the very low-level images doing some sort of a comparison and get the depth. So you do fusion first, and then you do recognition. So there's a question of whether you do monocular recognition and then fuse, or you fuse the images and then do binocular, that is, given the fused images, do the recognition. So back in the 60s, a psychophysicist named Bela Ulys wanted to look at this question. So to test this, he made a pair of synthetic images that were obtained by essentially spraying black dots on white objects. All right? So here's a notional description, comes from the Forsyth and Ponce book, of sort of putting, imagine that those are white and you sprinkled pepper, you sprinkled black dots all over the whole thing, and you took one picture from this side and another picture from that side. What you'd get are these two images, okay? Now, when you look at those two images, you don't see anything in there. But if I showed them to you in stereo, which is very difficult for me to do here, you would actually see that block raised, all right? So what we can do is we can animate those. We can animate random dot stereograms in the same way that we animated the swimmer. I don't have animations of this one, but I do have animations here of this. Well, if you look at this for a little while, I hope you'll see a shark. Does everybody see the shark? Okay, so this is the head sort of sticking out, then it bends around, and then the tail sticks out again. So you'll notice I just drew that tail, okay? But, of course, the tail is not in any individual picture. It's only in understanding the difference between them. Now, this was actually done from what's called an autostereogram website. You can go take a look. There are ways of making these so that if you can use the same picture, cross your eyes, or stare at them differently, that you'll get different images in the two eyes. But I think you get the idea that from these two images, you can see the depth. And what's interesting is if I present one to one eye and one to the other, you see that depth. So the answer to Ulij's question was whether you process the image first, finding these regions, and then line them up to do the stereo, or you first line up the sort of little local pixel area in order to do the stereo. It's clear that you do that first. That you do the stereo first. You don't have to have any specific objects or region. Sort of a clean way of saying it is that human binocular fusion, fusing the two together, is not based upon matching large-scale structures or any individual process of the image. It's actually based on a low-level process that directly fuses the two images. So now let's think about the geometry of stereo and get to the mathematics. The basic idea is this. If I have two cameras, and remember cameras are defined by their optical centers, all right, and they're both looking at some scene point, if I can figure out which 2 points in the two cameras are the same point, and furthermore, if I can tell which way, if I know something about which way the cameras are pointed, then I can figure out the depth of that point. That's it. So for estimating the depth between the stereo, remember the shape between the two views, there are two things we have to consider. First is information on camera pose, and sometimes referred to as calibration. How are the cameras oriented in space with respect to each other? And the second is on image point correspondences. That is, which point corresponds to which. So here you see the red dot in the two images, left and right, are both corresponding to that front corner. What we're going to do is we're going to swap that order. We're going to talk about doing the image correspondences first, because that's the what you're going to do for your problem set, and it's the fundamentals between stereo matching. And then we save calibration for later, because calibration is also used for a whole bunch of other types of geometric processing that we're going to do with the cameras. What we're going to do is we're going to step through the geometry for a pretty simple stereo system. The first thing we're going to do is assume that the optical axes are parallel. That's these right here. And because the optical axes are perpendicular to the image planes, it means the image planes are parallel. In fact, we're going to assume that they're exactly coplanar. So this image drawn here is as if we were looking down on our camera rig system, right? The cameras are looking out, okay, and this is the image plane right here, so we're looking down on the plane. And that will let us take a look at how things shift left to right in the stereo imagery. For our geometry here, we're going to assume our cameras are separated by a baseline B, and that both cameras have a focal length of f. So f is on both sides. So for the two cameras, they both have the same focal length. Now, let's assume that we have some point P in the scene, okay? And it's located at a distance z in the camera coordinate systems. Now remember, the z is the distance all the way down to the centers of projection. Okay, so that's z, not to the image plane, but to the center of projection. And if you remember, just for mathematical convenience, we put the image plane in front of the center of projection so things don't get inverted. So that point P projects into both the left and the right images. Now, just to make sure you're paying attention, on the left image, the distance is going to be positive, and on the right image, the distance is going to be negative because our origins are right in the middle. 0 is here is in the middle of the image plane. Got it? So distance is positive on the left and negative on the right. these quantities XL and XR are meant to be distances, so they're positive values, but whether they move plus or minus depends upon which image we're in. So here's our point PL, and there's our point PR. And PL is, as I said, this distance XL to the right of the optical axis, so it's positive. And the point PR is to the left, so it's negative XR to the left of 0. All right? So now we can do some simple geometry to figure out the relationships between X's, P's, B's, P's, and everything else that happens to be in the picture. We want to find an expression for Z. So we start by using similar triangles, just like we did for projection, but these are different triangles, the ones looking down. We have the first triangle, which is based upon the point P and each of the projections. That triangle is shown in yellow. And then there's another triangle that's based upon the center of projections and the point P, and that one is shown here in blue. See how it faded in? Let me back it up. There it is. That's the other triangle. Well, we now have two similar triangles, so we can write down what the relationship is between the edges, namely that B minus these distances, so that's going to be this distance, okay, is to this distance, which is just Z minus F. That's same proportion as the total baseline B, I'll draw it here, is to the total Z. Okay, those similar triangles give us that relationship. So a very little bit of rearranging gives us an expression for Z that says that Z is equal to F times B over XL minus XR. Okay, and that difference between the left and the right amount, that's called the disparity. The cool thing here is that we're computing the distance in the scene based upon a difference between these two. Now, you should ask yourself a little question here. What happens when disparity is 0? Well, when disparity is 0, that means that some point in the scene projected to the same point in the left image as the right image. In other words, as I moved from my left to my right camera, that point didn't appear to move. Well, remember we had a quiz on this. We talked about how come the moon follows you. Well, the moon follows you because Z is so far away that you get no change in the left and the right. So the disparity is 0, so the depth is what? It's infinite. Okay? And that's the inverse relationship between disparity and depth.
Say I have two images from a stereo setup. One in which I have a tree on the right-hand side and a person standing in front of it a bit to the left. Stereo images are not very different. In the second image, I have the same tree, but the relative position of the person is a little different. Can you figure out which is the left image and which is the right image? Enter the word left or right in the corresponding box below each image. Here the left one is the left image and the right one's the right image. From the left image, we know that the person is standing in front of the tree. Now if you imagine the two stereo cameras, then you'll notice that the left camera is viewing the scene from a little bit to the left, vice versa for the right camera. Similarly, if we look at the right image and consider the two stereo cameras, same thing here. Now if we know that the person is standing in front of the tree, then the only combination that makes sense is that the left image is from the left camera and the right image is from the right camera. One way to think about it is the following. If you shift your viewpoint to the right, then objects that are closer will move further to the left than objects that are further away.
So here we're going to show you some example of disparity, okay? In the left-hand side, you'll see that there is a point at the bottom of this window, okay? And in this image on the right over here, and by the way, it took me a while to figure out which image was left and which image is right, and I did that by looking right up here at the trees. You can see that in the image on the right, the chimney has moved to the left with respect to the tree behind it, so that's the right image. What happened is, if I go to the same location in this image as in the first image, I don't land on the window. I actually have to move this far in order to get to that window point. That's the disparity. And in fact, you can build what's called a disparity map. For every point x, y, you can say what's the disparity. And you'll notice something about this disparity image, right? Notice that the stuff here is bright.